granularity. Okay, I discussed this last week. You have to consider communication overhead whenever you load share to all the tasks that is running on different processor or different cores. If it is on the same system, normally there is no issue because the communication backbone normally is very high, okay, in petabyte second. But if it is using networking to share the data, it can be a problem. So you have to consider communication overhead. Okay. The other one is latency and bandwidth. On a single system, normally we don't have this. Latency normally is very small. But bandwidth, we always have very large bandwidth. But if it is through communication media, then it can be slow. So you have to take into consideration whenever you do distributed parallel computing. Okay. The rest, I think you can refer to the link that I mentioned to you. I discussed last week already. Visibility of communication, meaning that how visible is it from your programming perspective. For MPI, this is invisible because MPI do the communication for you, so you don't have to know how it is transferred from one place to another. Okay, why visibility is important? Sometimes you need to know how it transfers. If it is not optimal, you want to go in and then rectify it. But if it is not visible to you, or if it is not accessible to you, you might not be able to do anything. So you have to rely on the platform that's given. Like for example, MPI, you have no choice. You have to rely on the MPI to do the communication for you. And then another consideration that we have to think about is the communication, whether it's synchronous or asynchronous. MPI actually has synchronous and asynchronous communication. What I've shown to you this week or last week, most of them are synchronous. That means you send and then you wait. Okay, you wait until completion before you proceed. But there is also asynchronous communication where you send the data and then while it is sending, you actually proceed on to do other tasks. You don't wait. Okay, waiting is bad. That's why we use asynchronous programming if you want to eliminate this wait. But of course, it adds into the complexity because asynchronous communication programming is actually quite confusing. Okay, because you have to think about sending while they're doing other tasks, and then you have to get back to the process to find out whether he has done it. So you have to check the status always. So it adds into the complexity when you do asynchronous. Of course, you want asynchronous communication, but at the same time, you do not want our program to be too complicated or very confusing. Okay, scope of communication, meaning that whether you are doing podcasts, do you do Skype together, do you do one-to-one? Okay, so you have to look into this as well. What kind of communication that you do. And then you also have to consider the efficiency of communication. Like what I mentioned just now, if it is not efficient, you want to increase the efficiency, okay, by reprogramming certain parts maybe. Okay, another thing about this consideration is this as well. Okay, the granularity of your problem. Okay, the granularity is basically an equation which shows up there is the computation divided by communication. Okay. So we have to consider if it is worth it to do parallel computing or not, depending on this. Okay, what we want is this to be high. High is good. Okay, I mean low is bad. Okay, so high also means coarse-grained parallelism. Coarse-grained parallelism forms parallelism. Okay, towards down here is low. This is a fine-grained parallelism. Okay, we don't want this, we want this. Okay, why? Because if your computation time spent to compute is more than communicate, that means you are more efficient, isn't it? Fair enough? If your time spent communicating, you do less computation, but your time spent in communication, then you'll be low. Okay, and we don't want that, and that is fine-grained parallelism. Sometimes you have no choice because of the problem, the nature of the problem can be in this direction or that direction. Okay, so if it's in this direction and you're no way, then it's not good. But if it is in this direction and you can go around it, that means you fix it so that you get coarse-grained parallelism, then it's good. Okay. So how does coarse-grained look like? Or fine-grained look like? Fine-grained parallelism is relatively small amount of computation work, but a lot of communication work. Okay, so the ratio is going to be low. Okay, because this is low, this is high. The overall is going to be low. The ratio is going to be low. Okay, and this requires a lot of communication. Why is it bad? It's because you compute a little bit and then you communicate. You compute a little bit and then you communicate, right? And maybe your communication is also very lengthy as well, and it's going to be bad. For example, here, this one is quite okay. Okay, the computation and the communication is more or less, but here you see communication is higher than computation, so it is quite bad. Right? Here is good, but this one is quite bad. Right? And coarse-grained parallelism, relatively high in computation, but the communication is low. So the communication is blue, is quite low, so the ratio is going to be high. So this coarse-grained parallelism is good. So you have to look into this as well, whether you can move into this direction. But as I said before, sometimes you cannot. For example, if you are doing physical molecular simulation, let's say some of you do molecular simulation, right? So you're highly dependent on other part of your molecules. So you need to communicate. Okay, you communicate with the task that is computing nearby. You ask for the information, the status, the temperature, or the kinetic energy. Because you need to find out your neighbor kinetic energy to find your average kinetic energy maybe, right? So you need to communicate quite a lot. So that will be fine-grained parallelism, okay? And it might slow down your computation speed. Okay, what are the other things to look out for? Is to reduce, if you want to improve your performance, reduce your I/O, input-output, because input-output is slow. Anything that dealing with input-output is going to be slow. For example, you're waiting for user key press, mouse movement, okay? Or you're reading from hard disk. Hard disk is going to be slow. It's secondary storage, right? So it's going to be a lot of time spent just to retrieve the information. So where's the best place to put it? Let's say you've got this situation. You can choose solid state hard disk maybe. Maybe solid state hard disk is faster. Or maybe you move into RAM completely. But of course you have to buy, you have to purchase the memory to store the information. Yep. We know that it's going to be costly, right? Secondary storage like a hard disk is going to be cheaper in terms of capacity, the price. Okay, so you have to look into that. Now rule number one, if it is involving I/O, you try to reduce as much as possible. If you can. Of course, most of the time you cannot. But if you can, try to reduce as much as possible. If unnecessary read, don't read. Okay, if you have access to parallel file system, try to use it. Okay, parallel file system is better because if you want a single hard disk, and this is going to be the bottleneck, right? Everybody is going to read from here. When it is serving this process 1, okay, process 2, process 3 have to wait. So this is bad. But if you have access to several hard disks, okay, then you can access them at the same time. So this is 1, 2, 3. Okay. If they are working on different data, then you better split them into 3 different hard disks. This is one piece of data, this is a second, which is different, and this is the third one different. And then they are processing on different data, they can access at the same time. Or, let's say they process on the same data, you still can split them, you just make a duplicate copy. That means you waste the memory. This one copy, this is another same copy, this is another same copy. So you got 3 copies altogether, you waste the space. But then in terms of computation speed, they can access in parallel, so it's faster. So these are the considerations you can do in order to improve your performance. Okay, another thing is if you want to write, please don't write like 1 byte, 2 bytes, no. You write one chunk, meaning that, let's say for example, normally what we do is we process right into the hard disk, process a little bit right into the hard disk. So this accesses is going to be slow because there are so many accesses here, and each one of them is going to be slow. The better one, it will be like this.